Patch antenna. What is a patch antenna? A patch antenna is a type of radio antenna with a low profile which can be mounted on a flat surface. It consists of planar rectangular, circular, triangular, or any geometrical sheet or patch of metal mounted over a large sheet of metal called a group plane. They are the original type of microstrip antenna described by Powell in 1972. The two metal sheets together form a resonant piece of microstrip transmission line with a length of approximately 1/2 wavelength of the radio waves. The radiation mechanism arises from discontinuities at each truncated edge of the microstrip transmission line. The radiation at the edges causes the antenna to act slightly larger electrically than its physical dimensions. So in order for the antenna to be resonant, a length of microstrip transmission line slightly shorter than 1/2 the wavelength at the frequency is used. The patch antenna is mainly practical at microwave frequencies, at which wavelengths are short enough that the patches are convenient and small. It is widely used in portable wireless devices because of the ease of fabricating it on printed circuit boards. Multiple patch antennas on the same substrate, called microstrip antennas, can be used to make high-gain array antennas and phased arrays in which the beam can be electronically steered. A variant of the patch antenna commonly used in mobile phones is the shorted patch antenna or planar inverted F antenna, usually called PIFA. In this antenna, one corner of the patch or sometimes one edge is grounded with a ground pin. This variant has better matching than the standard patch. Another variant of patch antenna with a partially etched ground plane, also known as printed monopole antenna, is a versatile antenna for dual band operations. Microstrip or patch antenna are becoming increasingly useful because they can be printed directly onto a circuit board. Microstrip antennas are becoming very widespread within the mobile phone market. Patch antennas are low cost, have a low profile, and are easily fabricated. Consider the microstrip antenna shown in Figure 1, fed by a microstrip transmission line. The patch antenna, microstrip transmission line, and the ground plane are made of high conductivity metal, typically copper. The patch is of length L, width as W, and sitting on top of a substrate, some dielectric circuit board of thickness which is H, with permittivity. The thickness of the ground plane or of the microstrip is not critically important. Typically, the height H is much smaller than the wavelength of operation, but should not be much smaller than 0.025 of a wavelength or 1/40th of the wavelength, where the antenna efficiency will be degraded. Geometry of microstrip or patch antenna. The frequency of operation of the patch antenna of Figure 1 is determined by the length L. The center frequency will be approximately given. The above equation says that the microstrip antenna should have a length equal to 1/2 of a wavelength within the dielectric or substrate medium. The width W of the microstrip antenna controls the input impedance. Larger widths also can increase the bandwidth. For a square patch antenna fed in the manner above, the input impedance will be on the order of 300 ohms. By increasing the width W, the impedance can be reduced. However, to decrease the input impedance to 50 ohms often requires a very wide patch antenna, which takes up a lot of valuable space. The width further controls the radiation pattern. The normalized radiation pattern is approximately given. In the above, K is the free space wave number given by 2 pi over lambda. The magnitude of the fields is given. Figure 2. Normalized radiation pattern for microstrip or patch antenna. The directivity of patch antennas is approximately 5 to 7 decibel. The fields are linearly polarized and in the horizontal direction when viewing the microstrip antenna, as in Figure 1a. Next, we'll consider more aspects involved in patch or microstrip antennas. Fringing fields for microstrip antennas. Consider a square patch antenna fed at the end as before in Figure 1a. Assume the substrate is air or styrofoam with a permittivity equal to 1 and that L is equal to W and it is equal to 1.5 meters so that the patch is to resonate at 100 MHz. The height H is taken to be 3 cm. Note that the microstrips are usually made for higher frequencies so that they are smaller, much smaller in practice. When matched to a 200 ohm load, the magnitude of S11 is shown in Figure 3. Figure 3. Magnitude of S11 versus frequency for a square patch antenna. Some noteworthy observation are apparent from Figure 3. First, the bandwidth of the patch antenna is very small. Rectangular patch antennas are notoriously narrow band. The bandwidth of rectangular microstrip antennas are typically 3%. Secondly, the microstrip antenna was designed to operate at 100 MHz, but it is resonant at approximately 96 MHz. This shift is due to fringing fields around the antenna, which makes the patch seems longer. Hence, when designing a patch antenna, it is typically trimmed by 2 to 4% to achieve resonance at the desired frequency. The fringing fields around the antenna can help explain why the microstrip antenna radiates. Consider the side view of a patch antenna, shown in Figure 4. Note that since the current at the end of the patch is 0, which is open circuit, the current is maximum at the center of a half-wave patch and theoretically 0 at the beginning of the patch. This low current value at the feed explains in part why the impedance is high when fed at the end. Since the patch antenna can be used as an open circuit transmission line, the voltage reflection coefficient will be 1. When this occurs, the voltage and current are out of phase. Hence, at the end of the patch, the voltage is at a maximum. At the start of the patch antenna, the voltage must be at minimum. Hence, the fields underneath the patch will resemble that of Figure 4, which roughly displays the fringing fields around the edges. Figure 4. Side view of patch antenna with E field shown underneath. It is the fringing fields that are responsible for the radiation. Note that the fringing fields near the surface of the patch antenna are both in the Y plus direction. Hence, the fringing E fields on the edge of the microstrip antenna add up in phase and produce the radiation of the microstrip antenna. This paragraph is critical to understanding the patch antenna. The current adds up in phase on the patch antenna as well. However, an equal current but with opposite direction is on the ground plane, which cancels the radiation. This also explains why the microstrip antenna radiates, but the microstrip transmission line does not. The microstrip antenna's radiation arises from the fringing fields, which are due to the advantageous voltage distribution. Hence, the radiation arises due to the voltage and not the current. The patch antenna is therefore a voltage radiator, as opposed to wire antennas, which radiate because the currents add up in phase and are therefore current radiators. As a side note, the smaller piece of R is, the more bowed the fringing fields become. They extend further away from the patch. Therefore, Using a small permittivity for the substrate yields better radiation. In contrast, when making a microstrip transmission line where no power is to be radiated, a high value of E sub r is desired so that the fields are more tightly contained or less fringing, resulting in less radiation. This is one of the trade-offs in patch antenna design. There have been research papers written with distinct dielectrics. Different permittivities are used under the patch antenna and transmission line sections to circumvent these issues. Number 1 question. The shape of the patch in rectangular microstrip antenna is? The answer is A. The explanation. The antenna is named under the shape of the patch. For a rectangular microstrip antenna, the patch shape is rectangle. For a general microstrip antenna, patch can be any shape like rectangle, circular, elliptic, and triangle. The second question is, in microstrip antenna, the patch and feed line is photo etched on dielectric substrate. Is it true or is it false? The answer is A, true. Because microstrip antenna is a printed antenna which is fabricated using photolithography technique. Its design process consists of a ground plane and a dielectric substrate in which patch is created. The source is connected to it through a feed line by photo etching process. Third question. Which of the following is the most common version of the printed antenna? A. Horn antenna. B. Microstrip antenna. C. Wire antenna. D. Lens antenna. The answer is B, because microstrip antenna is a printed antenna. It is fabricated using photolithography technique. It consists of a radiation patch on one side of dielectric and a ground plane on the other side. The patch can be of any shape like circular or rectangular. The fourth question is, in which of the following type of antenna a patch is created during fabrication? A. Microstrip antenna. B. Horn antenna. C. Wire antenna. Or D. Lens antenna. The answer is A, because in microstrip antenna, patch is created on the dielectric substrate using photo etching. The shape and size of patch may vary the return loss. Horn, wire, and lens doesn't have any patch. Horn is a waveguide antenna and a wire antenna is made of dipoles. The fifth question is, which antennas are known as patch antennas, especially adapted for spacecraft applications? Is it A. Aperture, B. Microstrip, C. Array, or D. Lens? The answer here is B. Microstrip. Advantages and disadvantages of patch antenna. We have 5 advantages and 5 disadvantages. In advantages, the number 1 is lightweight and low volume. Second one is it is easy to fabricate. Easy to feed, such as coaxial cable, microstrip line, etc. It is easy to use in an array or incorporate with other microstrip circuit elements. Mechanically robust when mounted on a rigid surface. In disadvantages of patch antenna, number 1 is narrow bandwidth. Low efficiency limited by conductor and dielectric and surface wave losses. Low gain. Radiation from feeds and junctions. Lower power handling capacity. Main applications: mobile and satellites, global positioning system or GPS, radio frequency identification or RFID, wire interoperability of microwave access or WiMAX, medical applications, radar applications. Summary. A theoretical as well as practical aspect of microstrip patch antenna is presented. Lower gain and lower power handling capacity can be overcome through an array configuration. Particular microstrip patch antenna can be designed for each application, and different merits are compared with conventional microwave antenna.